Hello everyone, we're now in week 2 of the radiation protection course. Now we will be focusing on radiation's interactions with the body. The objectives for this unit includes a summary of photoelectric effect, Compton interaction, ionization, excitation, and any factors that influence the probability of these interactions occurring with matter. I'm sure that you've learned about these concepts and these processes in other courses as well, but this is a good review and it drives the message home. So this course is named Radiation Protection and Radiobiology. So what does radiobiology really mean? It is the study of the effects of ionizing radiation on living systems. X-ray absorption is an example. X-ray absorption in biological tissue follows fundamental physics concepts and processes of interaction between radiation and matter. Medical radiographers and students in the field, such as yourselves, require a basic understanding of interactions and processes that we use to optimally select the technical exposure factor, such as the kV and the MAS. We know for kVp, this is the energy level of the photons in the X-ray beam that's going to interact with the patient. And we know that the MAS is the product of the electron tube current and the amount of time in seconds that the X-ray tube will actually be activated. So both of these factors are important because the energy that is being transmitted to the patient per unit mass is contributing to the patient's overall absorbed dose. Remember from the last lesson that X-rays are a man-made form of ionizing radiation that comes in the form of electromagnetic energy. The higher the frequency of that radiation, the higher the penetrating power. Now, the time in seconds that the X-ray tube is activated is the main determinant of how much radiation is actually directed towards the patient during the X-ray exposure. But because we can control the exposure factors, and by that I mean the kVp that controls the penetrating power of the X-ray beam, and the time in seconds that the X-ray tube is actually activated, which by the way is the main determinant of how much radiation is directed towards the patient during the X-ray exposure. So once again, because we can manipulate these factors, like kV and MAS, it becomes our responsibility to ensure that we minimize the dose to the patient, ensuring that they get as low as is reasonably achievable during an examination. It is important that you know how to manipulate the exposure factors for the benefit of the patient and ultimately minimizing their dose while producing a good quality X-ray. So for this module, we need to summarize the process of ionization. As mentioned in the previous lesson, ionization is the process by which an atom or a molecule acquires a negative or a positive charge by either gaining or losing an electron. When this happens, the element changes its characteristics and it evolves into something else that is potentially damaging because it is now chemically reactive or unstable. So the resulting electrically charged atom or molecule is called an ion. Basically, if you have more protons than electrons in an element, it has a positive charge and is a positive ion, or what is referred to as a cation. If you have more electrons than protons in the element, it has a negative charge and is a negative ion, or what we call an anion. It is important to remember that ionization will only occur if the electromagnetic radiation has high enough frequency and enough energy capable of removing the electron from the atom. If ionization does occur, it can lead to the production of free radicals. So if the affected atom or the molecule is necessary for normal function of an organism, then the entire organism may be at jeopardy and may be affected. Although ionizing radiation is important to us and valuable for creating diagnostic X-ray images, it is important to note that it does cause or can cause damage to some biological tissue. So now let's look at the process of excitation. While electrons typically remain in their prescribed orbital levels, it is possible for an electron to be knocked from its orbit into another level. So a bombarding or incident electron or photon can collide with a bound electron, raising it to a higher energy level. and it starts dancing around in excitement, so to speak, as it is now in a state of excitation. Why? Because it has gone from a lower energy state to a higher energy state. So naturally, when all the excitement dies down, the electron wants to return to its ground state and it wants to move back to its orbital level, as it is attracted to the nucleus of the atom. So the excitation energy stored in the excited atom is normally released in the form of light or X radiation. So electrons, because they're not completely removed from the atom, they are just in a higher energy state, and the atom will gain energy or become excited during this process, and that's why it's called excitation. Both the processes of excitation and ionization can lead to the production of free radicals. So a free radical is an unstable molecule. Typically, it's highly reactive and short-lived. They can damage the cells in your body. So they form when atoms or molecules gain or lose electrons, like through the process of radioactive decay and ionization. You can also be exposed to free radicals that comes from the environment, such as the solar radiation, too much suntanning on the beach, or you could be exposed to it through cigarette smoking or other air pollutants. Perhaps you live close to a nuclear power plant. When X-rays do interact with the atoms within the body, one of three things can happen. Either there's no interaction and the X-rays pass straight through, or there's partial absorption with some scatter. Scatter involves partial transfer of energy to the tissue, with scattered rays having less energy and a different path than the initial incident photon. Or there could be complete absorption. If an interaction occurs that transfers all of its energy to the body, then the amount of energy absorbed per unit mass is called the absorbed dose. The more energy received, the greater chance of biological damage. So let's try and minimize that energy as much as possible. That being said, without absorption, it would not be possible to produce a diagnostically useful image. So there always has to be a balance between the benefits of the procedure and the risks of the procedure, and the benefit always has to outweigh the risk. So when you have a large number of photons, it's really hard to predict the interactions these individual photons will have on the biological matter when it enters the human tissue. However, it is possible to predict what will happen on average, and this is adequate enough to determine the characteristics of the image that will result from these interactions. When an X-ray beam passes through a patient, it goes through a process called attenuation. Attenuation is simply the reduction in the number of primary photons in the X-ray beam through the process of absorption and scatter radiation. Now, the optimal X-ray image is formed when only direct transmission X-ray photons reach the image receptor, but we know in reality in clinical situations that scattered photons do reach the image receptor and degrade the image quality and the sharpness of the recorded image. So next we'll be looking at photoelectric absorption, which is one of the most important processes in X-ray formation. This absorption process requires a photon energy range of 23 to 150 keV. It's the most important interaction between X-rays and the body, and the interaction occurs between an X-ray photon and an inner shell electron of an atom. So incoming X-ray photons interact with the electron. It transfers all of its energy to the electron, and the photon then completely disappears. So that electron that is sitting in the inner shell that received the energy from the incident photon is now completely knocked out of its orbit and set free from the atom. And when this happens, it's called a photoelectron. The photoelectron is absorbed within a few seconds by another atom. The absorbing atom now has a negative net charge, and the original atom has a positive net charge, and an ion pair is formed, and the potential for damage then begins. So in the photoelectric interaction, once again, the tissue atom is ionized. These photons are of low energy and will be absorbed by the body. And this absorption of the photon energy is the patient dose, the absorbed dose. So absorption or photoelectric absorption increases patient dose and it increases biological damage. The probability of the damage occurring to the body will depend on the energy of that incident X-ray photon. The atomic number of the tissue is very important when it comes to atomic when it comes to absorption or photoelectric absorption, because absorption will increase as the energy decreases and the atomic number increases. The amount of biological damage caused by X radiation is closely related to photoelectric interactions because as the number of photoelectric interactions increases, the radiation dose or the absorbed dose received by the patient also increases. So it goes without saying that as the absorbed dose increases, the potential for biological damage is there, and it does increase as well. So how about those Compton interactions, which we commonly refer to as scatter radiation? They definitely increase patient dose. It not only increases patient dose, it also increases dose to ourselves as technologists. And that's why we do not stand near the patient undergoing the radiographic imaging procedure, because the rays can be scattered towards us and in all directions. Compton scattering can occur at any point as the X-ray photons leave the X-ray tube. So they can be scattered by the parts of the equipment, such as the filters, the X-ray tube housing, the table, the floor, anything that these rays may strike. Shielding is therefore of utmost importance. Shielding with lead aprons and gloves, especially for us as technologists working with a patient. With regards to Compton interaction, the process involves an incoming X-ray photon interacting with a loosely bound outer shell electron, transferring some of its energy to the electron and then setting that electron free, allowing that electron then to interact with other atoms and create ions. This electron eventually loses its energy or enough energy due to numerous collisions and recombines with another atom that may need an electron. So how can we decrease scatter radiation? Well, we can do that by decreasing the kilovolts. But in doing so, by reducing the kilovolts, we also increase the number of photoelectric absorptions. And we know that photoelectric absorption is equivalent to or increases the patient dose as well. So we have to be sure to select factors and weigh our variables and choose the correct balance between image quality and patient protection. So what is the probability of interaction with matter, with the body? Let's look at these various factors. So mass density, that's number one. Body density and atomic number are important in determining attenuation. For example, if radiography is performed at an equal thickness of bone and soft tissue, the bone, which is approximately twice as dense as the soft tissue, will absorb about 9 times as many photons in the diagnostic energy range as will the soft tissue. We also have to consider the atomic number of the atom we're dealing with. For example, calcium, which is found in bones, has an atomic number of 20. So it undergoes much more photoelectric absorptions than the equal mass of soft tissue, maybe, or air for that matter, because air has a effective atomic number of 7.6. The higher the atomic number of the tissue, the higher the probability of their interaction with the matter. We know, for example, that air absorbs far fewer X-ray photons, and this permits more radiation to reach the image receptor, giving it that blackened appearance, right? So whereas bone is well demonstrated in diagnostic images, as it absorbs more photons and makes it easier to see on the X-ray image. Now, the difference in absorption properties, this is another important factor. This means that the ability to distinguish amongst different body structures in an image will depend on the amount of X radiation these structures allow to pass through them and reach the image receptor. The less a given structure attenuates radiation, the darker it is, and vice versa. Also, the greater the difference in the amount of photoelectric absorption, the greater the contrast in the image will be. That is, between structures of the body. Without that photoelectric absorption process, there is no image to evaluate. So now you can understand why this plays such a crucial role in image production. And last but not least, contrast media also enhances absorption properties by increasing the atomic number of the structure and making it easier to visualize on the X-ray image. This, of course, also increases the patient dose. So in summary, there are many interactions that contribute to the image formation process. and you should have a good understanding of these processes. So this marks the end of our presentation. I've included some review questions, and we'll move on to the next one shortly.